So at this point, we will discuss Thevenin's theorem and Norton's theorem. But before we delve any deeper, let us contemplate on the image right here. So this image has two parts. We have fixed circuit elements and we have the variable element, in which in this case is a potentiometer or the load. Now this type of circuit can be found in so many electrical appliances, maybe some of which is available at your household. Like for example, an air conditioning unit. So in an air conditioning unit, you can see one or two knobs from which you can adjust things like settings, low cool, high cool. At the same time, we have a separate knob for the thermostat of an air conditioning unit. So beneath that control, what is beneath of what you're seeing in your actual aircon unit is the type of circuit that is depicted in this image. So the knobs that you are seeing in your air conditioning unit is actually a potentiometer, in which you can turn it clockwise or counterclockwise according to the setting. But what it is doing in the circuit is that it adjusts the resistance of the entire circuit connected to it as some sort of control or load control. So a potentiometer is also known as a variable resistor. So the resistor can increase or decrease accordingly. And this is the part on which is the variable element. The rest of the element is fixed. All of it are embedded on the integrated circuit board. So once again, we have fixed circuit elements and we have variable circuit elements. Now, there are many types of circuits which are complex in general. The type of circuits that we are solving so far are very simple and are meant to uh, teach you the basics of circuit analysis. But in real life, circuits are highly complex and interconnected to each other. Like for example, the circuit board in your mobile phones, in your computers, are meant to be compact and highly interconnected so that the size of the device will be small. But even if they are complex and compact and interconnected, there are circuit elements on that circuit board which are meant to be a variable element. So when the variable element is adjusted, parameters such as voltage or current across each element in the fixed circuit is also changed. So it often occurs in practice that a particular element in a circuit is variable, as what I've said, while other elements are fixed. As a typical example, a household outlet terminal may be connected to different appliances constituting a variable load, such as an aircon. Each time the variable element is changed, the entire circuit has to be analyzed all over again. So that's a very hassle. So to avoid this problem, there are Thevenin's theorem and Norton's theorem that provide a technique by which the fixed part of the circuit is replaced by an equivalent circuit. So we will simplify the fixed part of the circuit using Thevenin's or Norton's theorem. And these are powerful tools for circuit design. And from what we've discussed previously, superposition principle and source transformation are prerequisites to learning both Thevenin's theorem and Norton's theorem. So that's how important these two circuit theorems are in real life. So what we're gonna discuss first is Thevenin's theorem. So Thevenin's theorem is a circuit analysis tool used to simplify the fixed elements in a complex circuit. This theorem states that a two-terminal circuit, aka what you can see in the diagram below, can be replaced by an equivalent circuit denoted as letter B. So this will be our equivalent circuit consisting of a voltage source VTH. So we have voltage source labeled as VTH, and this VTH is known as the Thevenin voltage, in series with a resistor RTH in this diagram, which is also known as the Thevenin resistance. Thevenin voltage VTH is the open circuit voltage at the terminals of the fixed circuit. So VTH is the voltage across the terminals A, B if it were to be open circuited, while Thevenin resistance RTH is the equivalent resistance or the looking back resistance at the terminals A and B. So if we are gonna measure the voltage and the resistance across the terminals A and B, the voltage would be known as the Thevenin resistance and the Thevenin voltage, and the resistance would be known as the Thevenin resistance. So there's no better way to illustrate to you the Thevenin theorem through an example. So this will be our example for Thevenin's theorem. In this problem, we have to find the equivalent Thevenin circuit and then find the current through RL when RL is equal to 6 ohms, 16 ohms, and 36 ohm. So RL in this diagram has a arrow across the resistor symbol next to it. So this is actually the symbol for a potentiometer or variable resistor, as what you can see in this picture. So a potentiometer or a variable resistor element is actually a two-terminal device in which the third terminal is just a ground terminal or a hanging branch. So that's a potentiometer. So we are gonna find the Thevenin equivalent of this particular circuit diagram. So our Thevenin equivalent has both RTH or the Thevenin resistance and VTH or the Thevenin voltage. So for RTH, we should turn off all sources. So when we turn off all sources, the voltage source, which in this case is 35 volts, will be short-circuited, while the 5 ampere current source will be open-circuited. So that is what we did with in the superposition theorem, but only in this case they will be turned off all at once. So to redraw the circuit, we have the voltage source will be short-circuited, then we have the 35 ohm resistor, then we have the 35 ohm resistor again at the middle branch, then we will open circuit the current source, Then we have another 35 ohm resistor here. Then that's our terminals A and B. And to illustrate, this is our Thevenin resistance, or our looking back resistance, the resistance that we can measure from terminals A and B. So this redrawn circuit is a combination of series and parallel circuit. So RTH will be the parallel sum of the 235 resistor, and then in series to another 35 ohm resistor. So we have 35 ohms plus the parallel sum of two 35 ohm resistors. We have 35 times 35 over 35 plus 35. And as simple as that, our Thevenin resistance is equal to 35 plus 17.5, which is equal to 52.5 ohms. So that's the first part of our solution. Now, for VTH, the way that we solved our VTH, reminding you once again that VTH, this is our VTH. Our VTH is the voltage across the terminals A and B. So we are gonna solve it as it is, but I am just gonna redraw the circuit. So we have once again the 35 volt voltage source. We have the 35 ohm resistor on top, the 35 ohm resistor, and in the middle branch we have the current source over here. So that's 35, then this is 5 amperes, and then we have another 35 ohm resistor over here, and those are our terminals A and B. So we are gonna measure VTH over here. Just gonna erase this. So looking at the diagram, we can solve this by mesh analysis. Mesh analysis with a current source. So we have our first mesh here for I sub 1, and then our second mesh here would be I sub 2. So for our mesh 1, we can obtain the equation negative 35 plus 35 I sub 1 plus 35 I sub 1 minus I sub 2 is equal to 0. So that's for equation 1. But in our second mesh, or for current I2, we have the presence of a current source which is 5 amperes but opposes in direction to the current mesh current I sub 2. So we will have to write I2 is equal to negative 5 amperes, and that becomes our equation 2. So what's gonna happen next is you will just substitute I2 on equation 1. So to continue, negative 35 plus 35 I sub 1 plus 35 I sub 1 minus 35 times negative 5, and that is equal to 0. We have 70 I sub 1, 35 plus 35 is 70 I sub 1, and that is equal to moving 35 times 5 and another 35 to the other part, to the other side of the equation. We have 210 divided by 70 I1 is equal to 3 amperes. Now, how do we solve VTH from this current I sub 1. So I sub 1, we can obtain the current across this, let's say I sub 3, across the middle branch. I sub 3 is equal to I sub 1 minus I sub 2. So this is similar to this one over here. Our VTH actually is equal to the voltage across the 35 ohm resistor over here, because parallel voltage elements in parallel have the same voltage. So VTH then is equal to 35 ohm, specifically this branch over here. Wait, changing it to red. Specifically this branch over here, we have 35 times I sub 3. No, we don't actually need to write this in. I sub 1, I sub 3 being equal to I sub 1 minus I sub 2. So I sub 1 is equal to 3 minus I sub 2, which is equal to negative 5. And our VTH then is equal to 280 volts. So that's the second part of the solution. Now that we have our VTH and our RTH, we can redraw the circuit into its equivalent Thevenin diagram. So the Thevenin diagram will look like this. We have VTH as the voltage source, which is 280 volts, in series to RTH, and our RTH is equal to 52.5 ohms. And then we have another resistor from the original problem, and this will be our RL. So the current that flows through RL will be known as simply letter I, small I. So the way that we can solve I is, first we have to write a formula for Ohm's law. We have I is equal to voltage source 280 volts over 52.5 plus the resistor in series to it, which is RL. Now that we are asked to write to solve for the values of current as RL is changed from 6 ohm to 16 ohms to 36 ohms, we can obtain three values for our current. So first, at RL is equal to 6 ohms, our I is equal to 280 volts over 52.5 ohms plus 6 ohms, and that is equal to 4.786 amperes. So just to box it, so at the second value of our RL, we have RL is equal to 16 ohms. Our current then is equal to 280 volts over 52.5 ohms plus 16 ohms, and that is equal to 4.088 amperes. And lastly, when our RL is equal to 36 ohms. The value of current would be 52.5 plus 36, and that is equal to 3.164 amperes. So as you can see, as RL increases, the current that passes through it also decreases. So there we have it, the three values of I as well as our Thevenin equivalent diagram. The next the next topic to tackle is Norton's theorem. Norton's theorem is very similar to Thevenin's theorem. In fact, Norton's theorem is found 43 years after Thevenin's theorem, and that Norton's theorem is also based from Thevenin's theorem. Only that instead of having a Thevenin voltage VTH, we will instead derive the Norton current IN with Norton resistance RN as our equivalent. So it states that a two-terminal circuit, the same as what you are seeing here, can be replaced by an equivalent circuit, which is represented in letter B, consisting of a current source IN, also known as the Norton current, in parallel with resistor RN, which is also known as Norton resistance. Norton current IN is the short circuit current through the terminals of the fixed circuit, terminals AB, while Norton resistance RN is the equivalent resistance or the looking back resistance at the terminals. So, however, from the concept of source transformation, it is interesting to note that the Thevenin resistance RTH of the equivalent circuit is equal to the Norton resistance RN of the same circuit. So since they are for both Thevenin's and Norton's theorem, the equivalent resistance is the looking back resistance. They are essentially equal to each other, and because of that, you can convert the Norton equivalent circuit from the Thevenin equivalent circuit using the following formulae. So since we've found out that the Norton resistance is equal to the Thevenin resistance, we can also derive the current, the Norton current IN, simply equal to Thevenin voltage VTH over Thevenin resistance RTH. So again, these formulae were derived because Norton's theorem was discovered 42 years after Thevenin's theorem, owing concepts from the latter. So in essence, Norton's theorem is very similar to Thevenin's theorem, only that instead of voltage, we are dealing in this time a current source. So to illustrate an example, we have this diagram, and we are gonna solve for the Norton equivalent circuit. So to start with, we will solve for Rn in the same way as we solve for RTH. We will turn off all sources, voltage and current. So to redraw the circuit, we have an open circuit to replace the current source, plus a short circuit to replace the voltage source, so the 35 ohm resistor remains in the middle branch. Then we have another 35 ohm resistor above, 35 ohm resistor below, and 35 ohm resistor across the circuit, and our terminals A, B. So we have So we have 4 resistors in total. And what we can do next is we can add all this series plus this one in parallel to it. So our Rn then is equal to the parallel sum of 35 plus 35 plus 35 times the resistor 35 across to it, all over 35 plus 35 plus 35 plus 35. So just to put it all in one equation, so we have the resulting Norton resistance is 26.25 ohms. So that's the first part of the solution. Then to solve for IN, or the short circuit current, let us redraw the circuit. So we have the current source over here, which is 2 amperes. We have the resistor 35 ohms in series to the voltage source 12 volts. We have resistor above 35, resistor below 35, then resistor across it 35, and we have terminals A and B. So by inspection, again, we can solve this equation by mesh analysis. So let's draw this as our mesh, first mesh current I1 and the second mesh current I2. But since we are gonna solve for IN is actually the short circuit current across the terminals A and B when the terminals A and B are short circuited. So please take note that when a terminal when this terminals A and B is short circuited, this practically means that the element across it, which is in this case is the 35 ohm resistor, is no longer significant. We will exclude this resistor because of the short circuit IN. So to continue with our solution, because of the presence of a current source for mesh 1, we can directly derive the value of I1 as equal to 2 amperes. Now this will be our first equation. Now let us obtain the equation for mesh 2. We have negative 12 plus 35 I sub 2 minus I sub 1 plus 35 I sub 2 plus another 35 again I sub 2, and that is all equal to 0. Negative 12 plus 35 I sub 2 minus 35 I sub 1, which is equal to 2 amperes, plus 35 I sub 2 plus 35 I sub 2 is equal to 0. So we have 35 I sub 2 times 3, we have 105 I sub 2 is equal to, moving this constants on the other side of the equation, we have 82 divided by 105. Then our I2 is equal to 0.781 amperes, and this will be our short circuit current, or our Norton current, I sub n. So that's the second part of the equation. As you can notice from the diagram, I sub 2 is actually equal to I sub n, the short circuit current. So now that we have both values, we can now obtain the Norton equivalent current. Equivalent circuit rather. So we have to draw the current source, which is our IN. Then we have our Norton resistance, our RN. Then we have our terminals A and B. Once again, our RN is equal to 26.25 ohms, and our IN is equal to 0.781 amperes. So this is the equivalent Norton circuit. But if you're gonna solve this using Thevenin's theorem, then that is also fine, provided that you will use these formulas right here. So you can actually derive Thevenin equivalent diagram from the Norton theorem, Norton equivalent diagram from the Thevenin equivalent diagram using this relevant equations or formula. The next thing that we will discuss is the maximum power transfer. So as I've mentioned earlier, we have this fixed circuit elements, and we have the variable element, which is the potentiometer. So the potentiometer, which is the knob, for example, in your air conditioning unit, controls the power for the entire aircon. So going back here, circuits are sometimes designed to supply and control power to a load. For example, a knob from the image above. So just going back here. So this knob or this potentiometer is meant to control the power for the entire circuit, for the entire fixed circuit. In circuit analysis, there are instances where we need to calculate the maximum power that can be delivered to the load. So why is this? So why do we need to calculate the maximum power? First is to reduce energy losses. So once we increase the limits of the voltage and the current that is flowing through the circuit, we can reduce the energy loss. And second is to determine the limits of the designed circuit. So this is important when you design a circuit, because circuit elements have their capacity, and you should not overload the circuit elements, because if the circuit elements becomes overloaded, then that becomes a problem, such as overheating, and worse of it, there will be fire in our circuit, and we want to avoid that. So that's why we need to calculate the maximum power transfer, so that we will know that our circuit elements remain at the bounds of their capacity. So looking back at the Thevenin equivalent circuit, just to go back here, so this is our Thevenin equivalent circuit. The power delivered to the load would be equal to P is equal to I squared RL, or equal to VTH over RTH plus RL squared times RL. So this is essentially the formula for our power. P is equal to I squared R. We can determine the maximum power by differentiating P with respect to RL. So we will owe the derivation of this formula from the maxima minima concept in differential calculus, which I assume you have already undergone. But for the interest of time, I will not show you the derivation the differentiation of P with respect to RL. And in fact, you can find this in the textbook. So if we are gonna derive this equation, wait, no, if we are gonna derive this equation, then we can equate that to dp, the derivative of P can be equated to 0. So that's how we observe the concept of maxima minima. To cut the derivation short, simply put, we can obtain RTH is equal to RL. So this is the condition of the maximum power transfer. So the maximum power transfer happens when the Thevenin resistance is equal to the load resistance. Like, for example, in our Thevenin example, if our RTH is equal to, if our RL is equal to our RTH, then maximum power transfer happens. But in this particular example, we've only solved for the value of RL, which is at most is 36 ohms. So 36 ohms is still less than our RTH, which is 52.5 ohms. So at RL is equal to 36 ohms, the maximum power transfer does not happen or does not occur yet, because RL must be equal to our RTH. So substituting RL for RTH on the power formula here encircled in red would yield the maximum power, or P max, is equal to VTH squared over 4 RTH. So this will be our formula for maximum power transfer. So just a tip over here, in our assessment for maximum power transfer, we will solve for the value of RL, which will yield the maximum power. Then solve for the value of this maximum power, and this is what we are gonna do in our example for maximum power transfer. So we will find in this particular example, we will find the value of RL, which will yield the maximum power, then calculate this maximum power. So we have this diagram is very similar to what we have solved in our Thevenin's theorem, and we will borrow the results for RTH, which is equal to 52.5 ohms. So from previous example, RTH is equal to 52.5 ohms. So for maximum power transfer, RL should be equal to RTH, which is equal to 52.5 ohms, since we have solved this already in our previous diagram, in our previous example. So that's the value of RL, which will yield the maximum power. Now, what we're gonna do next is we will calculate the maximum power. Maximum power using the formula P max, or maximum power, is equal to VTH squared over 4 RTH. And our VTH from previous example, borrowing again, our VTH is 280 volts. So let's write 280 volts squared over 4 RTH, which is in this case equal to 52.5 ohms. Our P max, our maximum power, then is equal to 373.33 watts. So that's That's the value of our maximum power. So in our assessment later, what's gonna happen is that you will calculate the maximum power transfer after the Thevenin's uh, after the Thevenin's theorem in the same circuit problem, so that we can just borrow the results from our previous calculations. And there you have it. This will be our lesson 6 for this particular course. I hope that you have learned so far how to simplify complex circuits, and if you have any questions, please don't hesitate to notify me, and I will also send you a PDF copy of the sample problems that we have obtained for this lesson. So thank you so much, and please stay safe.